Alright guys, today we're going to discuss an old but classic topic, how LINQ affects Unity performance. People have been discussing LINQ's pros and cons everywhere, better readability and easier maintenance. It simplifies queries, makes code concise. But beware of the cost. With the GC costs on the rise, memory allocation spikes, causing frame rates to dive. Every time Unity performs the gc.alloc, it allocates memory on the managed heap, typically in small chunks like 25 kilobytes, 27 or something. Once the total allocation hits a certain threshold, Unity will trigger its garbage collector. But here's something important. Unity uses an incremental GC system, meaning it splits the collection process across multiple frames. This helps avoid the long single-frame pulls by traditional system.gc.collect in C#. So don't manually call gc.collect. That will block the main thread and hurt your game's performance. Let's jump into the code and the Unity profiler to see what this looks like in practice. I prepared two scripts for A/B test. I'm going to evaluate how different coding styles impact memory allocation and GC behavior in Unity. I defined a few public fields. Rotate speed is the angular speed for rotating each cube along the x-axis. Cubes is the list that stores all the generated cube game objects for iteration and manipulation. Cube count represents the number of cubes to instantiate at the start. Float Y and Z just for camera settings. The goal is to simulate a dynamic environment with a large number of objects moving and interacting, which allows us to observe memory allocation patterns and the potential GC overhead in real time. Inside the update function, each cube does two things every frame. The first one is rotation. Each cube rotates along the x-axis using transform.rotate. The second one is proximity query. The code checks which other cubes are within 10 units of distance using a LINQ query. The lambda expression, which captures the external variables such as this.gameObject and the transform.position. This results in heap allocation due to the creation of temporary delegate instances and closure classes. Additionally, toList forces immediate evaluation and allocates a new list each frame. These per frame allocations are visible in Unity Profiler under gc.alloc and may trigger incremental garbage collection once the threshold is exceeded. Back in the Unity editor, I've created a game object called script loader for loading the script. I set the rotate speed as 50 and the cube count as 200. We have to build and export the game to test because it'll be much more accurate than testing in Unity editor. Go to the profiler and make sure uncheck everything except for the garbage collector under the CPU usage section. This will ensure that only GC allocations are visible. As the game runs, you will notice that a GC is being reported each frame. When running the game, you can pause the game and look for frames with performance bottlenecks. The red blocks indicate CPU active time greater than 16.67 milliseconds, which corresponds to FPS dropping below 60. When you select one of these frames, press A to frame it and press F to zoom in. You will see many deep red sections. These represent gc.alloc events. Next, you can right-click and show it in the hierarchy to inspect the allocation in more detail. As I mentioned earlier, the gc.alloc events indicate temporary memory allocations made each frame. You can see gc.alloc is called 1000 times per frame and it allocates 78.1 kilobytes of memory. This high frequency of allocations increases the GC pressure, causing frequent garbage collection cycles. In this script, we've introduced a static list game object nearby. This is an optimization to avoid creating a new nearby list every frame. In the update method, we first call profiler.beginSample to start profiling the performance, then use a for each loop to iterate through all the cubes. During each iteration, we clear the nearby list, ensure it only contains cubes that are within 10 units of distance during this frame. We use a for loop to check all the cubes. If the distance between another cube and the current one is less than 10 and it's not the same cube, we add it to the nearby list. The goal of this approach is to avoid creating a new list every frame via LINQ, which reduces GC overhead. And using a static nearby list, we minimize memory allocation and collection. After building the game and running the test, we can observe that the garbage collection results, unlike with the LINQ, there are no sharp spikes in the profiler. When selecting a frame, we can continue by focusing on it and showing it in the hierarchy. Here under the distance test section, there are no gc.alloc calls, indicating there was no memory allocation during this frame. We can also notice the running time of the frame, which is approximately 9.19 milliseconds. By scrolling up the mouse, we can confirm that the entire frame doesn't contain any gc.alloc calls, providing a cleaner execution path with minimal memory allocation overhead. In summary, for occasional queries on small collections where performance isn't a critical concern, you can use LINQ, but you must avoid using LINQ in frequent calls like update, fixed update, or performance critical code, as it creates temporary allocations and can trigger frequent garbage collection, affecting frame rate.